Hi, my name is Wesley Kaizer and I'm going to present the paper Sequence Operator Counts with State Space Search, written by Kaizer, Pereira and Ritt, from the Federal University of Rio Grande do Sul of Brazil. First, I'm going to present an introduction about the research topic. The paper Sequence Operator Counts by Davis and others introduces a decomposition for the planning problem into a master problem and a sub-problem. The master problem solves an operator count integer program, and the sub-problem tries sequencing the operator counts from the master problem. The main motivation for this decomposition is the primary solution, that's used to obtain the operator counts used in the sub-problem, and contains more information than the objective function value. The following figure illustrates this decomposition, in which we have the master problem that generates an operator counts that's used in the operator count sequencing sub-problem. If the operator counts is sequenceable, the corresponding plane is saved. Otherwise, the sub-problem generates a generalized landmark constraint that's returned to the master problem. OPSEC uses a SAT solver to solve the operator count sequencing sub-problem, encode the planning task and the operator counts in a SAT formula. If this formula is satisfiable, OPSEC is able to extract a plan. Otherwise, OPSEC uses a set of assumptions to generate the constraint to the master problem. Now I'm going to introduce OpSearch, that's the new method presented in this paper. Heuristic search is the most common approach used to solve classical planning tasks optimally. OpSearch is a new algorithm that uses heuristic search to solve the operator count sequencing sub-problem. Since it's based on heuristic search, OpSearch can use information from the search graph, such as the f-values of the states. This approach can generate smaller and more informed constraints, and can improve directly from advancements in planning research. Now, I'm going to press the rule used by OpSearch to generate the constraint when the operator counts is not sequenceable. This is the rule that OpSearch uses to generate the constraints. We generate a bound literal informed that the count for operator O must be greater than its current value if there exists a transition from an expanded state S to a generated state S' by the application of operator O, such that the f-value of state S' is less than or equals to fmax, that is the objective value from the operator count integer program, and or we don't have the count variable for operator O in state S, but the operator cost is greater than 0, or the count variable for operator O has value equals to 0. We don't generate bounds for zero-cost operators, and they are applied freely during the search. Now, I'm going to present an example for OpSearch using this rule to generate the constraints. In the first iteration, let's consider that the master problem returned an operator counts with a count equals to 1 for operator O1 and the fmax value from the objective function equals to 1. The following figure illustrates the state space that could be generated. The node N0 is the initial state and the node N8 is the goal state. For this iteration, the constraint learned informs that the objective value of the operator count integer program must be increased to 3. This constraint is learned from the initial node N0 that has a f-value equals to 3, that's greater than the current fmax. If this constraint is added to the master problem, the solution for the second iteration could return an operator counts with count equals to 3 for operator O1 and a fmax value equals to 3. In this case, we could generate nodes N1 and N2 by applying operators O0, O0', and O01. Operators O0 and O0' can be applied since they have zero costs. The constraint learned in this iteration informs that the count for operator O3 must be greater than or equals to 1, or the fmax value must be increased to at least 4. The bound for operator O3 is learned from the transition from N2 to N5, since the f-value for n5 is 3, that's less than or equals to the current fmax value. And the bound for fmax is learned from the transitions from n1 to n4 by the application of operator O2, and from n2 to n3 by the application of O0. Since both states have f-values greater than the current fmax, we can use the minimum of these values, here 4. In the third iteration, we could have an operator count with a count equals to 2 for operator O1 and the count equals to 1 for operator O3 and fmax equals to 3. With these operator counts, we can generate a new state n5 by applying operator O3. The constraint learned is similar to the one learned before. The bound for operator O2 is learned from the transition from node n5 to n8, since the f-value of n8 is 3, equals to fmax. And the bound for fmax is learned again from nodes n4 and n3. In the last iteration, we could have an operator count with counts equals to 1 for operators O1, O2, and O3, and the fmax value equals to 3. With these operator counts, we could generate a new state n8, that's the goal state. And we have a plan with operators O1, O3, and O2. Now I'm going to present a theorem for upsearch. The theorem states that for a solvable planning task, an operator count CS, a fmax value such that the modified A star of upsearch with an admissible heuristic function 8 cannot sequence CS, the algorithm upsearch always returns to the master problem an admissible constraint that does not remove feasible solutions. Now I'm going to present the results for upsearch. The first result shows that upsearch is better than upsec. Using all the instances from the IPC of 2011, we can see that upsearch solves more instances than upsec, that upsearch solves less subproblems than upsec, that upsearch has a better total solve time than upsec, that upsearch uses less memory than upsec, and upsearch generates smaller constraints, including on average 6% of the operators, while upsec includes on average 20% of the operators. In summary, upsearch is better than upsec, since it solves more tasks, solves less subproblems, uses less memory, and generates smaller constraints. Now, comparing only the 50 instances solved by both methods, the results show that upsearch solves less subproblems than upsec, that upsec had a better total solve time than upsearch in this case, but upsearch still uses less memory than upsec and generate smaller constraints. These results confirm that upsearch is better than upsec, since it solves more tasks, solves less subproblems, uses less memory, and generates smaller constraints. The second result shows that upsearch improves with better heuristics. Using all the instances from the IPC from 1998 to 2014, in which we could compute 8 star, we can see that upsearch with 8 star solves less subproblems, as the heuristic function is more informed. That upsearch with blind had a better total solve time. That upsearch uses less memory when the heuristic function is more informed, except for 8 star. That upsearch generates smaller constraints when a more informed heuristic function is used, and that upsearch solves more tasks when a more informed heuristic function is used. In summary, as a more informed heuristic function is used by upsearch, the number of subproblems solved, the memory usage, and the size of the generated constraint decrease, and the number of solved tasks increases. Now I'm going to talk about the applications of upsearch. The results of this research are also relevant in practical applications. For instance, our algorithm upsearch could be used as an end-time method to obtain lower bounds on planned costs. In agile planning, for which informative heuristics are already known, and in diverse planning, that aims to find several plans while guaranteeing diversity between them. Now, the take-home messages. First, we showed that the operator count sequencing problem can be efficiently solved using heuristic search algorithms. Second, our approach opens new research directions related to specialized methods or heuristics for the problem of sequencing operator counts. And third, this problem is a novel research problem with great potential of development in both areas of operation research and artificial intelligence. With this, I finish the presentation. Thanks for listening.